Next, we're going to look at an application of the Nernst equation, something called a concentration cell. I've diagrammed a concentration cell for you here on screen. Notice that the concentration cell is rather interesting in that there's copper, in this case, serving as the oxidation half cell, and there's also copper serving as the reduction half cell. In all of the cells we've seen in the past, it's always been two different metals, one on one side, one on the other. But in the case of a concentration cell, it's the same metal, the same half cell on either side with one important difference. In this case, in the oxidation half cell, the concentration is quite low. And in the case of the reduction half cell, the concentration is different. Thus the name concentration cell. Concentration cells operate as a result of differences in concentration. One thing that can be carried over, though, from what we've learned having to do with other cells is that the identification of reactants and products, assuming the cell has been properly designated or put together with oxidation appearing on the left and reduction occurring on the right, we can identify the various things as reactants and products in just that way. And as a reminder, don't forget that we've got oxidation occurring on the left and we have reduction occurring on the right. All right. So, understanding the concentration cell in this way permits us to write out the net cell reaction, where everything that is a reactant is on the left-hand side of the arrow, and everything that is a product is on the right-hand side of the arrow. And so all of the reactants in this case, well, the solid copper is certainly a reactant, and the other reactant is the concentration of copper 2+ ions. And their concentration is, I'll just write it in here, 1.00 molar. All right, and so there are the two reactant species. Now, the product species, the copper ions that have the 0.1 molar concentration, as well as the solid copper. There's the net cell reaction. Notice that as this reaction occurs, the concentration of the reactants in blue, the copper ions with a 1 molar concentration, that this concentration, as it is the concentration of a reactant, the concentration of this is going to decrease. And the concentration of the product, on the right-hand side, that concentration is going to increase. We can track these changes in concentrations in the following way. We can use a bar graph to designate these concentrations at various points throughout the cell and its operation. On the left-hand side, the concentration of the cell starts out at 1.0 molar. And on the right-hand side, the concentration of the copper ions starts out at 0.1 molar. Again, we have a lot of reactant and not very much product. And in fact, what will happen is the reactant will be used up. And a moment later, the concentration of the reactant may have actually been decreased to 0.8 molar. And you might be wondering then, well, if the concentration of the reactant drops by 0.2 units, then how should the concentration of the product change? Well, the product ion concentration should go up by the same amount because, in this case, we have a 1-to-1 mole ratio that relates the disappearance of the copper on the left with the appearance of the copper ions on the right. Consequently, if the concentration of the reactant goes down to 0.8, then the concentration of the product goes up to 0.3 molar, an additional 0.2 molar in concentration. Eventually, what will happen as these concentrations drop on the left and increase on the right, they will eventually reach a common point, a point where their concentrations are the same. The concentration on the left will be a value of 0.55 molar. The concentration of copper ions in solution on the right will be 0.55 molar. And these two concentrations When the concentration of reactant has dropped to 0.55 and when the concentration of product has increased to 0.55, the cell stops operating. A simple way of determining, as long as it's a 1-to-1 ratio, a simple way of determining the final concentration is simply to average the two concentrations that we had to begin with. And so the average concentration is equal to 0.100 plus 1.00 divided by 2, and that comes out to be 0.55 molar, the final concentration, at which point the concentration cell stops operating. But again, recall that this is only when the mole ratio is a 1-to-1 mole ratio, as it is here. And so this cell, as it operates, converts a higher concentration of copper ions into a lower concentration of copper ions, at least as far as the reactants are concerned. And as far as the product copper ion concentration, which begins low, its concentration increases. These two change, one dropping, the other increasing, until their concentrations are exactly the same. We can imagine this and review a little bit of thermodynamics if we imagine initially, what is the entropy like? What is the randomness or disorder like? Now, in one container, in volume 1, we had a solution of copper ions whose concentration was equal to 0.100 molar. And in the second container, call it V2, we had a solution of copper ions whose concentration was 1 molar. Now, thinking back to thermodynamics and this sort of process in the past, we can imagine that we only have maybe just one particle in one volume where the concentration is lower, and we have quite a few more particles in the volume that has the higher concentration. And what we need to do is consider how this compares to the final situation. So we'll call this finally. Now, finally, V1, which initially contained a low concentration of copper ions, its concentration now is quite a bit higher, 0.55 molar. And with dots, we can say that we have a few more dots than we had to begin with. On the other hand, the reactant concentration, which was originally in volume V2, its copper ion concentration has dropped to 0.55 molar, at which point the concentration cell stops operating. And we ask ourselves, as we compare the initial situation to the final situation, the initial situation with one particle in one volume and a bunch in the other volume, in comparison to the situation finally where we have the same number of particles, that is, the same concentration in either case, what is this telling us about the entropy? Well, the entropy is always greatest when particles are uniformly distributed. And so if we consider this process to be the process or the situation representing the final entropy, and this situation representing the initial entropy, we can say that the final entropy is actually greater than the initial entropy, as finally the particles, in this case the copper ions, are more uniformly distributed between the two containers. This, of course, is a sign of universal increasing entropy, and we would then think that this would contribute to a spontaneous process. In fact, in situations like this, we identify concentration cells as redox or oxidation reduction chemistry that are driven by increasing entropy. It is the increase in entropy which drives the concentration cell and is, in fact, what creates the electricity that one would expect to measure, the cell potential. Now, speaking of cell potential, we've talked about how the concentration cell actually operates, but we haven't determined the cell potential for this situation yet. And so what we need to do is we need to take another look at the Nernst equation. The Nernst equation, as you should remember, is an equation which we can use for calculating the standard cell potential, the cell potential, from the standard cell potential with this correction. Okay, so in this case, the Nernst equation undergoes quite an important change, as the standard cell potential in this case, which we would get by taking the standard reduction potential for the cathode, and subtracting the standard reduction potential for the anode. Why, going to the table, we realize very quickly that we would be taking the value for copper and subtracting from it, again, the value of copper, because we have copper in either case, and we see that this is just 0. In fact, this is always going to be true for concentration cells, in that we'll always be dealing with a cell that has the same element on the left as on the right, and so for concentration cells, the value, from the table anyway, is always going to be 0. Well, that's a nice simplification. We can carry that down here and say that now the cell potential for the concentration cell, anyway, is equal to a negative 0.0592 divided by n times the log of Q, which we can apply quite nicely now to our process, where it will be equal to a negative 0.0592. If you look at the net cell reaction, and obviously in this case it's copper being both oxidized and reduced, the number of electrons, actually n in this case, is equal to 2 in the case of this concentration cell. And then we have the log. Now, the log of what? We have to get this right. It needs to be the product ion concentration, so I'm going to just take a peek up here really quick to have another look. The product ion concentration was the 0.100 molar concentration, and so this should be 0.100 molar. That's the copper ion concentration that we've referred to as the product ion concentration, and the reactant concentration was 1.00 molar, just like that. Okay, and if you do the arithmetic, what you're going to find for this particular cell is that it does develop a small amount of electrical pressure or cell potential. Comes out to be equal to 0.0296 volts. Often such small voltages are converted into something called millivolts, again using the standard metric convention of milli, and so this would be 29.6 millivolts, a small amount of electrical pressure being developed by this thing that we call a concentration cell. Now, before we finish off concentration cells, let's just have a quick look at an application of a concentration cell. Okay, a simple application, and this application happens to be something that we could call an ion-sensitive electrode. And what I'll do is I'll simply diagram this situation for you so that you can see the way in which it would be used. We'll do this with an abbreviated cell diagram, where on the left I'll put a solid copper electrode, and that solid copper electrode is going to go into a solution that contains copper ions that are aqueous. But the thing about this is that in this particular solution, we don't actually know the concentration of the copper ions. So what kinds of solutions might we be talking about here? We could be talking about a sample of tap water. Tap water contains a small amount of copper. We could be running tests on lake water. Another material that might have copper ions present. The idea being that this particular cell has a solution that contains copper ions, but whose concentration is unknown. And that's something that we hope to solve for here in just a moment. Now that's half of the concentration cell. The other half of the concentration cell, recall that in science you never like to have anything more than one variable. And currently I have one variable, the unknown concentration of this copper ion solution. And so on the right-hand side we have copper ion concentrations, another copper half cell, aqueous, and this copper half cell has a solution whose concentration is 1.00 molar. I picked 1 molar just because it makes the arithmetic work much nicer. And we have that half cell also in contact with a solid copper electrode, just like that. Okay, so what we do is we create these two beakers, one that contains a known concentration of copper on the right, where reduction will occur, and one that contains an unknown concentration of copper on the left, where oxidation will occur, and we hook them up to our voltmeter for some additional information. And as I've said before, the electrons move through the wires in that fashion. And what we observe on the voltmeter face is 0.040 volts of electrical pressure. And this is an important piece of information that we can now use to determine the unknown concentration of copper ions in the tap water, or lake water if you like. So we turn to the Nernst equation. And the Nernst equation, recall, for concentration cells is quite a bit simpler than what we've seen. The cell potential is equal to a negative 0.0592 divided by n times the log of Q. Now, we know that in this case, the cell potential is actually 0.040 volts. That was simply the cell potential as measured from the voltmeter. We also know that in this case, as it is copper that we're working with, the value of n is actually equal to 2. Good? And then we have the log. And the log is the log of Q, as it was before, where the known concentration, the higher concentration, is 1.00 molar of copper ions on the bottom, and the unknown concentration of copper ions, I'll leave that as a question mark, is on the top. All right? And what we can do is rearrange this equation just a little bit and actually solve for the question mark. And I'll leave it up to you to do that. I'm running out of space at the moment. But what you should find is that if you solve for the question mark using inverse logs along the way, you'll find that the question mark, the concentration of copper ions in the unknown lake water sample, in this case comes out to be 0.0445 molar. In this way, concentration cells can be actually used and calibrated to determine the concentrations of, in this case, copper ions in solution, or in the case of a pH probe, hydrogen ions in solution.